The Dynamo and its applications. Observations of Faraday and Henry Magneto electric machines of Pixii, and of Saxton at Jorth's dynamo of 1855, Wills machine of 1866, Siemens of 1867 grams of 1867 grams of 1870 Tyson. As the means for furnishing electrical power, it stands today, the great fountainhead of electrical generation, and in its peculiar field ranks as of equal importance with the steam engine. Until about 1865, the voltaic battery, which generated electricity by chemical decomposition, was practically the only means for producing electricity for industrial and commercial purposes. It was through its agency that the telegraph, the electric light, and many other discoveries in electricity were made and rendered possible. Its constant limited amount of current, however, restricted the limits of its practical application, and although its current could furnish beautiful laboratory experiments, its mechanical work was more in the nature of illustration than utilization. But with the advent of the dynamo, electricity has taken a new and very much larger place in the commercial activities of the world. It runs and warms our cars, it furnishes our light, it plates our metals, it runs our elevators, it electrocutes our criminals, and 1,000 other things it performs for us with secrecy and dispatch in its silent and forceful way. But what is a dynamo? To the average mind, the most satisfactory answer would be that it is simply a machine which converts mechanical power into electricity. Attach a dynamo to a steam engine, and the power of the steam engine will, through the dynamo, become transformed or converted into a powerful electric current. Any other source of mechanical power, such as a water wheel, gas engine, wind wheel, or even a horse or man, will serve to operate the dynamo, its primary and sole function being to take power and convert it into electricity. The stepping stone to dynamo in its development was the Magneto electrical machine. This is a machine founded upon the general principle observed by Faraday in 1831 and 1832, and also by Prof. Henry about the same time, that when a magnet is made to approach a helix of insulated wire, it causes a current of electricity to flow in the helix as long as the magnet advances. If the magnet is passed through the helix, the current is reversed as soon as the magnet passes the middle point. The principle is the same if the magnet be made to approach and recede from the poles of an electromagnet having a helix wound around a soft iron core. Likewise, the same result occurs if the electromagnet with its helix is made to approach and recede from a permanent magnet, the current in the helix flowing in one direction when it approaches the permanent magnet, and in the opposite direction when leaving the said magnet. The movement of the two elements in relation to each other requires some force to overcome the repellent and attractive actions, and this force is converted into electrical energy. This is the principle of the magneto-electric machine. Saxton in the United States and Pixii in France were the first to produce organized devices of this class for generating electricity from magnetism. Pixii's machine, 1832, consisted of a permanent horseshoe magnet, which was caused to revolve in proximity to an armature upon which was wound a coil of insulated wire. On March 30, 1852, Sonnenberg and Rechten obtained a United States patent, No. 8843, for an electrical machine for killing whales, and on August 19, 1856, Spard obtained USP at Yo. 15,596 for the machine which came to be known as the Alliance machine. Both of these machines had permanent field magnets and were early types of magneto-electric machines. The efficiency of these magneto-electric machines was necessarily limited to the strength of the inducing field magnets, which, being permanent magnets, were a positive and fixed factor. Although the principle of the dynamo was clearly embodied in the Ajoff patent, its value was not appreciated until some time later. 11 years later, Wild U.S. Pat. No. 59,738, November 13, 1866. Employed a small machine with permanent magnets to excite the coil-wound field magnets of a larger machine. But Siemens British Pat. No. 261 of 1867, taking up the principle employed by Jorf, dispensed with his superfluous permanent magnets, having found that the residual magnetism, which always remained in iron which has once been magnetized, was sufficient as a basis to start the building up process. Farmer, Wheatstone, and Volley also recognized this fact about the same time. Siemens' patent also was the first embodiment of what is known as the bobbin armature. Graham and Divanois, British Pat. 1668 of 1870, and U.S. Pat. No. 120,057, October 17, 1871, were the first to bring out the continuously wound ring armature. Active development now began in various types and by various inventors including Weston, Rush Edison, Westinghouse and Housen, Westing-High-efficient, high-efficient, the revolving coils of the moles, the aerolales to the miles. When two are used, they are arranged on opposite sides of the armature and form what is known as the bipolar machine. A larger number constitutes the multipolar machine. The field magnets in the multipolar machine usually are arranged in radial position around the entire circumference of the revolving armature and are held in a fixed circular frame. To give a clear idea of the principles of the dynamo, the bipolar machine is best suited for illustration and is here given in figs 20 and 21, in which fig 20 represents the dynamo complete, and fig 21 a detail of the end of the armature and commutator. This armature consists of coils or bobbins of insulated wire, each section having its terminals connected with separate insulated plates on the hub, which plates are known as the commutator. When any section of the armature approaches the pole of a field magnet, the current induced in that section of the armature coils by the field magnet is taken off from a corresponding plate of the commutator by flat springs, seen in Fig. 20, and known as brushes. The field magnets A and B, Fig. 20, are shown with only a few turns of wire about them for clearer illustrations of the connections, which are made as follows. The wire A is extended in coils around the field magnet B, and thence around field magnet A, and thence to the upper brush on the commutator, thence through the wire coils or bobbins of the rotary armature, fan, thence through the wire brush to the wire. In this illustration, the circuit, it will passes through both the coils of the field magnets and the coils of the armature, involving the principle of mutual excitation. There are two principal kinds of dynamos, those producing the alternating currents, and those producing the continuous current. In the first, the current alternates in direction, or is composed of an infinite number of impulses of opposite polarity. One polarity when a section of the armature coil is approaching a north field magnet pole or receding from a south pole, and the other polarity when receding from a north field magnet pole and approaching a south pole. In the continuous current machine, the commutator and brushes are so arranged as to take up all the impulses of the same polarity and conduct them away by one brush, and gathering all the impulses of the opposite polarity and conducting them away by another brush. Thus, the current of each brush, in the continuous current machine, is always of the same polarity, and the polarity of one being always positive, and that of the other negative, the current flows continuously in the same direction. A third species of dynamo is the pulsatory, in which the current flow is invariable in direction, but proceeds in waves. A change in the character of the current generated by the dynamo is made by what is known as the transformer, in which the principle of the induction coil is made available. In this way, for instance, the high potential currents generated by the powerful water wheels at Niagara Falls are taken 20 miles to Buffalo, and are there transformed into other currents of lower potential suited to incandescent lighting and other various uses. A similar scheme is in process of fulfillment in the establishment of a water power electric plant near Conowingo, Maryland on the Susquehanna River to furnish electrical power to Baltimore, Wilmington, and Philadelphia. An important development in electrical generation and transmission is to be found in what is known as the polyphase, multiphase, or rotating current pioneer paytate, current pioneer paytates. 381,968, 381,969, 382,282,280, 382,282,282, analyzing the possibilities of the Dino, analyzing the possibilities of the Dino, analyzing the possible. I'd need see an idea. The criminal is strapped in the chair. Seen in Fig. 22. One terminal of the wire from the dynamo is strapped upon his forehead, and the other to anklets on his legs. And like a flash of lightning, the deadly energy of the dynamo performs its work. Not the least of the applications of the dynamo is its use in electrometallurgy for plating chemical reactions. The electric furnace, stimulated into higher heat by the dynamo than can be otherwise obtained, has brought about many valuable discoveries and made great advances in various arts. The metal aluminum and the hard abrasive or polishing and grinding material known as carborundum are the products of the electric furnace, and so is the product known as calcium carbide, which, when immersed in water, gives off acetylene gas and is a product now universally used for that purpose, and rapidly increasing in commercial importance. In Fig. 23 is seen the Atkinson electric furnace for producing carborundum. The electric current traverses the furnace through a series of horizontal electrodes at each end and highly heats a central core of carbon, which is disposed in a mass of silicious and carbonous material, and which latter is converted by the heat into silicide of carbon or carborundum. In Fig. 24 is shown a continuous electric furnace constructed as a revolving wheel under the To contemplate the dynamo with its clumsy, enormous spools, it suggests to the imagination of the average observer the gigantic toy of some Brobdingnagian boy. But the dynamo is no toy. It is the most compact, businesslike, and dangerous of all utilitarian devices. To touch its brushes may be instant death, for the dynamo is the prison house of the lightning, and resents intrusion. Hidden away from public gaze in some sequestered powerhouse, and working night and day like some tireless, dumb, and mighty genii, it sends its magnetic thrills of force silently through the many miles of wire extending like radii from some great nerve center through the conduits in our streets, and stretching from pole to pole like giant cobwebs through the air. Responding to its force, thousands of little incandescent threads leap into radiant brightness and shed their mellow and genial light in our offices, our stores, hotels, and homes. Brilliant arc lamps, rivaling the sun in power, make night into day and produce along our streets coruscations, silhouettes, and dancing shadows in spectacular and unceasing pageants. From the towering lighthouses of our coasts, its beams are thrown seaward, and a beacon for the mariner shines beyond all other lights. The great searchlight of our ships is in itself but a hollow mockery until the dynamo whispers in its ear the word light, and then its beam, reaching for miles along the horizon, discovers a stealthy enemy or signals the safe return to port. The mighty force of the dynamo entering the electric motors on the street cars turns the wheels and transports its load with scarcely a passenger inside realizing how it is all done. The same energy turns the electric fan, and with kindly service soothes the weary sufferer, and at another place remorselessly takes the life of the condemned criminal. The dynamo is one of the great factors of modern civilization, and its potential name, like that of dynamite, rightly defines its character.